Swayam Prabha. Digital India. Educated India.
All right, so we just have the one more, automobiles. It's time. So we've downloaded all of these, so they're in the download folder. So I just want to congratulate you all. It's amazing what you can do in a short time period in a short course, right? So you all, I know that these are not thorough assessments, but hopefully you did enough of all the different steps so that when it's time to do a thorough assessment, you know what you're doing. Is that okay? Yes? Yes, and you all had different data. So I just want to remind you, we're going to try to hold you to 10 or 10 plus minutes. Arun, are you going to be the timekeeper? Can you just wave your hand when it's 10 minutes? And then maybe we'll allow you to wrap up. But 12 minutes, you're done, right? Because we have to get through 7 of these and do other stuff too. All right? So who's first? Food waste management. All right. And so you can share the mic. This is easier, but it would be good to talk into the mic.
Very good morning, dear friends and faculty. This is our group. We have worked on the food waste management problem that was assigned to us. My team members, on my left, Dipali, myself, Himi, I have Ramanan and Sai Prasanna. So we have done our efforts to calculate do a life cycle assessment for a problem that was given to us. So the whole scenario here is we are talking of 386 kg food waste per day that is being generated at a place. So there were 2 options how this food has to be managed. The food waste has to be managed. So the first option was that the food waste was separated and transported about 4 kilometers on an on-site facility, which was an anaerobic digestion plant, wherein there were processes like primary storage, conveyor, grinder, conditioning tank, 2 digesters, a flare separator, digested storage tanks, and a control unit. From there was a biogas recovery system, which was covering the transportation of food waste to the plant. There was energy production happening in this method as well by a micro-sized cogeneration engine, and the utilization of energy was within the plant itself, and the transportation of the digestate, that is how the energy was being utilized, which was being generated in this cogeneration plant. So here the electricity used for this digester to work was 14.1 kilowatt hour per day, and the generation of energy was to the tune of 92.6 kilowatt hour per day. In comparison to this, our problem at hand was to do an LCA to compare this with another option wherein the food waste is being transported off-site to a landfill facility, wherein there was nothing that was being done to take care of the landfill. So to make it at par with the anaerobic digester option, so fossil fuel energy was being generated using natural gas. So what we found out from our life cycle assessment, whatever with the limited parameters we could do. So we calculated the greenhouse gas emissions for the scenario 1, which was the anaerobic digester. It came out to approximately 105 kilogram of carbon dioxide equivalent per day. And for the scenario of landfill, the emissions were to the tune of 154, along with some other toxic emissions of nitrous oxides, VOCs, NOx, SOx, and particulate matter. I would now hand over the mic to my teammate.
So I'll be talking about the flowchart which I have made. So first, the food waste are coming from various sources like industrial waste and household waste and farm waste and some food outlets and etc. So from the food waste, the collection of food waste is done based on segregation, and we'll be avoiding few citric based food waste for efficient biogas collection. And from that we are having 2 scenarios. The first scenario is direct landfill, and the second scenario is anaerobic digestion. Our problem statement was to cut off the fossil fuel usage in the landfill scenario. So here we'll be capturing the LFG, which means landfill gas, and we'll be utilizing the landfill gas for various purposes like energy and electricity and heat production. In the anaerobic digester, there are 4 units like primary storage tank, grinding and pre-treatment tank, and digestive tank. From anaerobic digester, like we are having 2, and biogas generation and digester. Digester is like it is kind of waste out of the biogas. Like after the biogas generation, it goes to the cogeneration plant for the generation of electricity. And from the digestate, we are having 2, solid digestate and liquid digestate. Liquid digestate is having like lots of toxic components in that, so it has to be again treated. So it is going for the waste treatment, and the leftover is being discharged. And the solid digestate can be treated and can be used as compost and for fertilizers for farming and etc. And from the biogas generation, through after getting our electricity from the cogeneration plant, again we are using it for the anaerobic digestion for a circular economy purpose. And these are our comparison of the 2 scenarios. And the transportation is from 66 km for the landfill, and for the anaerobic digestion, like it is near the wastage collection plant, so it is very low and 4 kilometers. And the methane emission comparison is for the landfill is too high, because in our scenario, like we are not capturing any like emissions out of the landfill. So like that is our idea to be worked on the improvisation the further. And the energy recovery is none in the landfill, and due to the anaerobic digestion, like we are having energy recovery as we are producing electricity out of it. And fossil fuel dependency is very high, because to equalize the electricity produced from the anaerobic digester, we are using fossil fuels for generating electricity in the landfill case. And the co-products are none in the landfill, as we know. And from the solid digester, we are getting compost and fertilizer and etc. And the total emissions are 154, which is very high, and 105.32, like quite okay.
So, looking at all the previous slides, we came to the critical ideas to improve the sustainability aspect of this. So, one was to reduce the GHG emissions. Second was to capture the methane emissions which can from the landfill and everything. And also to reduce the fumigative losses with efficient design of the AD and landfill process. Also to utilize the solid digest as fertilizers or the livestock bedding, and also the liquid digested with the treatment and releasing of the rest over. So these were the 5 ideas which were brainstormed by us. So first is to capture and process the methane gas out of the landfill as LFG. Second is growing bark-dwelling microorganisms on the plants so that it can capture the methane and from the atmosphere, and it can be used by them and transform it to the carbon dioxide. Third is flexible designing of the biodigester to solve the capacity of the solid waste availability. Like when there is less solid waste availability, the digester has some flexible design so it can run with smaller quantity, and when the availability of the food waste is high, the capacity could be increased. Fourth is to enhance the digestion process using some certain microorganisms or the poultry and cow dung waste, so it can enhance the digestion process inside the digester. And fifth is the overall efficiency of the anaerobic digester facility with the energy efficient fixtures, lightings and sensors, the control unit and everything. It's basically on the energy efficiency scenario. So to give a representative idea about the ideas, we got few pictures from different sources. Very first idea is to capture the methane gas from the landfill as LFG. Second is the bark microorganisms on the bark which can capture the methane and convert it into CO2. And then third is the flexible design of the digester, where you can see first is a very fixed roof, second is a floating roof. So I think it can go down and up as per the solid waste availability or the amount. Third is it's a horizontal placement of the digester. And the fourth idea is to enhance the digestion process with food waste with some microbes or adding the poultry and cow dung waste. Fifth is to increase the efficiency, overall energy efficiency. So based on these ideas,
For the suggested ideas from our group, we have taken these parameters as the criteria to evaluate the idea what we are suggesting here. So the parameters what we choose is first importance we have given to electricity generation, and we given a weightage of 5, and the to reduce GHG emissions we have given a weightage of 5, and digestate use 3, reducing toxicity 4, cost effectiveness 4, and public awareness and acceptance are 3. We consider these are main parameters because the main objective of our work is to generate electricity and to reduce GHG emissions and also to utilize waste without by maintaining the sustainable principles. So after awarding the scores, what we observed is our idea of 4 was taken the highest score, that is the enhancing the digestion process by using microorganisms and cow dung and poultry waste. And next best idea was to capture and process methane gas out of landfill as LFG. By working on these ideas, we feel that we will be able to address few of the problems and GHG emissions. Will try to reduce it. Thank you.
also we can add up, like we can combine 2 or 3 ideas together, like 1 and 2 can be combined in the landfill option, 3, 4, 5 can be combined in the anaerobic digester option.
And in anaerobic digestion, it was less, not like very much less. There is just a difference of 700 kg CO2 equivalent.
We had about 75 marks for energy efficiency of the entire facility, since there are sensors, lighting, fixtures, all those are there. So we did have one of that idea to enhance that part.
Our main focus was to reduce the emission out of the landfill, which is not been captured in any of the works, and to cut off the use of fossil fuels to generate electricity in the scenario 1 of the landfill, and to enhance the efficiency of the anaerobic digestion to produce more electricity, like with less amount of sources and so on.
Certain amount of biogas was again used for cogeneration of electricity, ma'am. We have sent back to electricity digestion plant only. So overall we have done it. Boundary was fixed only.
I would like to add one more thing. Like as you said, the difference is not that much big. In the landfill case, the emission is calculated only the emission out of the landfill. Like let's say like LFG gases are only the calculated thing. And the transportation, and the electricity out of fossil fuels. In the anaerobic digester case, like the whole process is been calculated. So like the process is very long. So the difference is not that much big.
Hi everyone, I am Shanawaz Haider. Today we will going to present a life cycle assessment of organic cotton sweatshirt. So basically I will give you a background about it, and later Gayatri ma'am will explain. So this organic sweatshirt is basically produced in India and exported to Europe. As we have yesterday we saw a ma'am class. Ma'am was talking about CBAM policies and carbon bound. Carbon bound. It is like very concerned about European policies and everything. So we have tried to comply with that. And from here, ma'am will explain. Sorry.
So first, like if we consider the project description, the one which we took up is with like organic cotton sweatshirt. So like it like the boundary condition given to us was like the sweatshirt is worn 2 times a week and it is washed once a week, and that too like the different components that constitute our sweatshirt is like organic cotton and brass zipper and the polyester tape to stick the zipper with the sweatshirt. So washing assumptions we have taken is the load for average load for washing machine was around like 3.8 kgs. So approximately the partial load was 0.794 kg with a water use of 2.92 liter. So this part has two other subdivisions. That is like you could go for after washing in drying section, you could go either for a line drying or you could use tumble dryer. So we have considered based on the environmental conditions prevailing, we considered like line drying could be used for 6 months and the other 6 months we could go for tumble drying. So if you consider that way, electricity use accounted to be about like approximately 41.6 kilowatt hour, and then the main condition to notice is that the cotton is grown and the garment is manufactured in India and then it is transported to Germany by sea or like by cargo and then it is used there. So there are certain losses during the manufacture phase, that is like 5% of the material is lost as pre-yarn, and then like when this yarn is converted to textile, 2.5% is lost up there, and at cutting section 12% accounts to be the waste. So transportation, that is like internal transportation either within like India or within Germany, additionally it accounts to about 2000 miles by truck, and then from India to Germany approximately like 11,400 kilometers by sea. So like the main goal of us is to do an LCA analysis for this pertaining conditions, and then the scope is to make a sustainable product which makes the EU regulations and CBAM. So the system boundary and approach we have took is cradle to grave. So our functional unit is 1 unit of this organic cotton sweatshirt. So this is the process flow of the entire thing, which is like from the cultivation of cotton to the end of life. So if you consider one more thing I would like to add is our main challenge was that it is already an organic cotton sweatshirt. So we have to further look up on the options that would reduce the impact of this product on the environment. So if you consider the cultivation of cotton, it the parameters of this system is that it could vary based on land, water consumption and organic manure we use and what equipment we are going to use for the cultivation of cotton. So whatever change is happening in these parameters will significantly have an impact on our cotton cultivation. So the main emissions that are being generated from this part is the one which is from equipment usage, which is mostly like air quality impact. And then comes the manufacturing of yarn part, where there are 3 factors like ginning, cleaning and spinning, and then from this fabric production is done. So there are 3 subdivisions in this manufacturing of yarn process. Organic sweatshirt could be either used like colorless or dyes. So in order to make our condition a diverse one, we have even gone for dyeing. So in dyeing also we could use like two types of options, like either we could go for conventional water based dyeing or CO2 dyeing. But if you consider this water based dyeing, you would end up in more emissions, that is like either as I think so mostly as water and as solid, but water could be handled because most of the companies operate based on ZLD techniques. And then this dyed fabric is also packaged, which includes the cardboard for packaging, and electricity for this automated packaging units will also be accounted here. Then this is knitted and made into a complete fabric, wherein this waste, mostly solid waste, which we told, right, pre-yarn, and then from yarn to next step that 5% wastage, and then cutting wastage would come here. And in all these steps, transportation will be there. Transportation is of 3 types, like local, that is within India, within India, where all it gets transported, it is denoted as L, and global, from India to Germany. and regional R stands for like within Germany, wherever we are just transporting our product, we are representing it as yarn. Then this fabric which we have made is made into an end product, and then it is transported globally and it reaches Germany. So here customer use comes, sorry, this is customer use, and then like customer use part consists of two things, like they should use it, they should wash it and dry it, right? So usage, I think so, like since it is a cloth, there won't be any wastage. If it is a food material or if it is something, there would be some wastage accounted. So since it is cloth, there would be no waste coming into picture during use phase. So when you consider washing phase, there would be like water and electricity involved. So drying, as I have mentioned earlier, we have taken line drying and tumble drying. So when it comes to next phases, like end of life, when it comes to end of life, there are like three options available to us. Like either we could reuse it, repurpose it, or we could dispose it. Reuse, like I think so it's possible, because like in countries like Germany and other like similar countries also, there exist thrift stores where you can just sell your used item at some lower cost. But repurposing, I am not sure whether like because their social condition is entirely different. So in India, like if you consider, we would repurpose a cloth to either rag or to something else. But I am not sure whether this part plays a major role. But we have included it for some diverse conditions. And then last phase is disposal phase. Disposal phase, like you could either make it end it up in a landfill, or you could incinerate it. But one thing to notice that is like incineration, some amount of energy could also be generated out of this process. So this is the overall process flow which we have accounted. And from here, I would like to hand over it to Shanavas.
Thank you, Gayatri, for explaining detailedly. Okay, after getting all these details, as we can see the life cycle stages, for each life cycle stages, there are different materials are there. We have quantified these materials and we have got some impact factors, and along with we have used recipe 2016, midpoint, hierarchist approach is a balanced approach, and because of that we have got 18 different impact categories that we have accounted. And the thing is, like as we can see this, I have considered as 1 lakh units have been sent from India to Germany, but we have for this as a functional unit is only one. So the impact, all these impacts are only for one T-shirt. This is all the, as we can see, these are all the impacts and units also there. Okay, after quantifying all those impacts, these impacts are transformed after quantifying the materials. It's multiplied with the characterization factor. Then we will get in impacts, environmental impacts. Then this environmental impacts then multiplied with some factors to convert from impacts to in impact category of different impact categories: global warming, stratosphere, ozone, ionizing radiation, fine particulate mass, freshwater eutrophication, marine eutrophication, terrestrial ecotoxicity, freshwater ecotoxicity, human carcinogenic, human non-carcinogenic, land use, mineral resource, fossil resource, water consumption. Okay. The outcome was that, like for conventional sweatshirts, it takes around 2,700 liters, but for the t-shirt we have tried to do a life cycle assessment. It consumes only 1,300 liters. These are the product design change we have included in a life cycle. Instead of going for conventional treatment of dye, we choose ECOOP technology. We will choose CO2 dyeing, and for CO2 capture in the entire process, we will use gas hydrate. Though it is now $65 for a ton, but on a mass-based scale, it will reduce in future for sure. We have some limitations that most of the data which was available with us was global data, and particularly the electricity is there. For India, we have used for the electricity for production, everything we have considered Indian electricity, and for washing we have considered the electricity from Germany. this conclusion we can say we can have a cotton t-shirt if we have from not only from manufacturing but also the customer use, as we have included 6 months tumble drying and 6 months line drying. It's in the hands of a customer to continue the sustainability and having to reuse, repurpose. It's not only from a manufacturer side, it's how we use it that makes a product sustainable. Thank you.
Good morning, everyone. Our main focus was to comparison between which is better, aluminum can or a PET bottle for carbonated drinks. Our functional unit is 500 ml of carbonated drink per can. We haven't mentioned it, but the product description is we are using 66% of recycled aluminum for aluminum cans and 7% of recycled PET for PET bottles. But we haven't considered 7% because we don't have the data available for it. We considered 100% ideal situation. And also at the end of the life, recycling is done. 75% of it is recycled and 12% is landfill and 13% is incinerated. This is the flowchart for aluminum can. First it is mined and then extraction of bauxite. After that heavy duty transportation occurs and then refining. After that aluminum oxide formation from which aluminum is extracted. During these processes there's a lot of use of water and the treatment of wastewater generated from this, and from the aluminum extracted the alloy required for making the aluminum can is made using different metals, and then can is manufactured using blow molding, and then filling of drinks, carbonated drinks, and then sealing, and then labeling and packaging occurs, and then distribution, then chillers. Chillers in the sense when we are sent it to retailing, they chill it and then sell it. So it's not storage but chilling occurring in the retail side, and then consumption from that. After that, after consumption, it's the end of life goes to three ways. They're either littered, and then some goes to landfill, some goes to recycling can bins. It's not a major case scenario, but many stores that are selling the aluminum can beverages have a specific can for recycling, but it's not a major case scenario in India. Then that landfill, from then it is incinerated. From collection, from recycled can bins, it is sent to collection centers where they are baled, and then some of the cans come back from later through rack pickers, and then from collection centers it goes to recycling centers, from which through recycling we get the aluminium which is shredded, and then from that bars are there which are further purified because it's an alloy, so we have to purify it to form again a little bit more purer, high grade aluminum, and from then making of aluminum bars which are again sent back to aluminum making to manufacture the cans again. This is for PET bottle. From fossil fuel extraction, from there we are the chemicals that we are needed for it are ethylene glycol and terephthalic acid, which are then polymerized and then extruded to mold them into the specific shape of the bottle we need. And polypropylene also, for our bottle the cap is made up of polypropylene, so the polypropylene is also used, and then filling and then packaging and distribution, and almost it is similar, but again we can have a reuse case in PET bottle, but this is not recommended because the bottles that are used for beverages are made to be single use, but there is still a reuse scenario there, so that we included that also.
We have seen the flow sheets for LC of aluminum cans and PET bottles. In this case, because PET bottles recycling we didn't consider because of limitations of data, but 66% of the aluminum cans are recycled and went back to again manufacturing. So this is the like embodied energy and emissions for aluminum can. In this, like 66% aluminum like recycled one, that is secondary source, and primary like 34% is considered. Around like this is considered like per can, that is the functional unit. So embodied energy here, it is for the material, like material, whatever the material we will get, including like extraction, mining, and then processing, everything that is costing more. And then transportation, we have considered almost like 542 kilometer transportation with heavy truck. And then landfilling and incineration is very, very less, almost like 0.00. So it's not showing in this. And then same, it is reflecting in the CO2 emissions as material, because materials are giving a more embodied energy, and so kg of CO2 emissions per can also more for materials. And then transportation, and then this is the PET bottle like embodied energy and emissions. This is also per PET bottle. It's almost, if you consider here, it's 1.1, and it is almost like 3 times more in getting materials, which might be including because of refining, extraction of fossil fuels, and processing. That might take too much of, because it's involving like ethylene glycol and terephthalic acid and polymerization, all those things. So that because of might be getting like materials processing itself is taking more of embodied energy. And then manufacturing, if we take maybe like if we consider like a recycled one, this embodied energy might come down, because we have already like PET. So by shredding and purification, then we might get, but I'm not sure, like again it can come back to by depolymerization, all those, but it can be useful for some other things like fiber, something else, but not for the PET bottle. So anyways, for production of materials it will be higher than aluminum cans, and same thing is reflecting in the kg emissions. Just want to show comparison, like materials, manufacturing, transportation, these 3 are major things. If we see like embodied energy per unit, means that is per can of aluminum or per can of per PET bottle, material is costing like for PET bottle is taking too much. And then CO2 emissions also they're much higher for the PET bottle, if we see in the manufacturing, materials, and transportation. Yeah, this Parvati will explain about the inferences taken from this. Like, inferences. These are the inferences, final inferences from this comparison. The total, like we have seen for aluminum cans is like 1.72 megajoules per can, and for PET bottles 4.8, almost like 3.5 times. PET bottle is consuming more energy, and 2.5 times emissions are there more in the PET bottle. So from this we can say aluminum cans are very better than using a PET bottle. But when I see in the stores, I always see only PET bottle, but I don't understand why aluminum cans are not there. Like, Milo will explain about impact, how it is impacting like environment.
So as we have seen from our 2 members here, so from extraction to till the end of life, so we have seen how it has different process has different kind of emissions, and we also have seen the percentage of both aluminum and the PET can bottle. So we have gathered common impacts which comes through the process, starting from the extraction, refining, manufacturing, and the distribution channels, and the use through our different channels of customers and retailers. So in the middle we can see different kind of emissions, CO2, NOx, SO2, particulate matter work. So these are the major common impact which we are getting from all this process, and this is harming our environment in terms of global warming, acid rain, particulate matters, and the ocean acidification. So there are these are some of the common which impact later on to human health, the biodiversity loss, and resource depletions. So as we know, like we cannot totally avoid aluminum and PET bottle. Yes, in the process, but as per our data, which we have seen is aluminum. Using aluminum is much better than PET bottle because it has a higher recycle value, and the percentage of impact is less. So further our recommendation and limitation, Parvati will explain.
Okay, so limitations, we had a lot of data which was not there for us. So because of that, we have also focused our impacts on the carbon dioxide emissions. And for when we considered the PET bottles, the recycling PETs, so chilling and transportation, all the data was not available. So we couldn't calculate the entire emission for the whole life cycle of the PET bottles. And even we had a few data that was missing for the aluminum cans as well. But then with the data that we have and that we have calculated, and the conclusion that we came to, that is aluminum cans is better option than PET bottles. We also tried to come up with some solutions to increase the sustainability using aluminum cans. That is, now it is 66% that is being recycled. That recyclability could be improved by optimizing the manufacturing process, and also by minimizing the extra coatings which are present on these aluminum cans, as we see. And they also have some kind of materials which are inside the cans, which are used as a way of preservation for the carbonated drinks. And also another thing, the transportation also, we found that there was an increase in the emissions. For aluminum cans, the transportation, the distance that it was transporting from the distribution to retail was about 542. So maybe rerouting and optimizing the distance or the between the distribution and the retail could also help in minimizing the emissions.
To transportation we have like use case, we don't have refrigeration, chilling, how that data is not there, so we didn't consider that. And we felt also recycling when we have seen, it is almost like incineration, all those things there for aluminum can, but for PET bottles it's not there. So landfilling of aluminum cans is very less, so it's mostly going for recycling. But for PET bottles we could not get the data, like how much it's going for recycling, landfill, all those things. So entire thing we have calculated only for the virgin materials. Like use case, definitely chilling and refrigeration is needed. It is electricity again. Again that electricity in India, again it's mostly like coal fired. Again most CO2 emissions and transportation also, all those things will be there. Most of the again CO2 emissions we will expect in the things. So more of coal fired again will give more of CO2 emissions. But again when we see the comparison, anyways we need use case will be same for the both the things, like PET bottles and aluminum cans. And finally we can say aluminum can still like better.
Good morning everyone. So our topic here is single use aluminum takeaway containers. So this is the description given for the container itself. So it has two components. One is the tray, which is 12.5 grams of the whole tray, out of which 40% is recycled aluminum, and we have a paper carton cover which is 10.8 grams with the LDPE lining of 0.5 grams. So the purpose or use of the item is mostly for ready to eat meals, or it can be used for single heating in the oven, and it's only for short term food storage and transportation and not for long term storage. And the as far as the LDP carton cover is considered, it's a light protective closure. It just helps in not the food not getting spilled, and also acts as a barrier by locking in moisture and the grease from the food. And we have the print surface on top, which is for branding and for user attraction, and also maybe include some instructions as to how to use it. So the critical design attributes of the product is the first is functional performance, of course. For that, we have heat resistance because aluminum helps in that. And the cover, like I mentioned before, acts as a barrier, and it also is a secure fit to keep the food inside the container. Next is strength and durability. So aluminum tray, even though it is very thin, still it has a structural rigidity. It can be when it is manufactured, it is flat as a sheet, and then it's molded into a container. Still, if it is thin, it still has structural rigidity. And the edges, if you remember, the edges of the container is rolled or crimped, so that it adds to the strength, and also it helps in the users handling it with ease. And the carton cover should be thick enough so that it doesn't tear when the person is using it, or when the person is packing in the food. And in terms of food safety, the products, the materials that we use, aluminum, the carton cover, or the LDP lining, they should meet the food regulations, and the surfaces should be smooth, and it should be non-reactive to the food, so to minimize contamination. And of course, sustainability or circularity is also part of design attributes. So the product already contains recycled aluminum content, which is 40%. And when we are trying to recycle it, we should be able to segregate the materials easily, which is also already there. The tray and the carton cover can be separated very easily for recycling. And in terms of aesthetics and user experience, it is already clean. It has a uniform appearance, and we have a printable surface which allows for customization, and also it is very lightweight, so it allows for ease of handling.
Moving on to the process flow diagram that we are constructing, we initially started with the initial starting from the raw material, manufacture, the extraction of raw material. And since we have 3 different classes of materials like the LDP lining, the paper carton, and the aluminum, we started with the extraction, all those processes, and further once these are acquired, we will be transporting it to the manufacturing unit, where for aluminum we will be melting it, and rolling, casting, all those will be done into that will be converted into aluminum container, and the LDP, which will be melted and rolled, and it will be converted into thin sheets, which means thin films, and on the paper carton it will be covered. And then once the product is made, it will be properly labeled and everything, and it will be sent to the distribution center, from where it will be further delivered to the retailer, from which it will be going to the end use. So since the data that we have obtained is limited, so what we have done is we have considered only the cradle to gate, or we have the data with respect to the raw materials, the manufacturing process as a whole, and the distribution center, the transportation, and the selling point transportation. So with respect to that, we have considered the analysis with respect to with respect to the values of energy and the CO2 equivalents. And among these categories, we are expecting this to come under the housewares and other category, where we expect the materials and manufacturing costs to be that is the relevant factor that comes into play. So we have done the analysis with respect to the energy and the CO2 equivalent, where our functional unit was 1 serving of takeaway container, one unit, and we have taken the aluminum virgin material, aluminum recycled, paper carton tray, and the LDP lining, and energy used for the entire manufacturing process was given as a data, and based on that we have calculated what is the energy required for that processing unit. And transportation, we have given the transportation from the manufacturing unit to the distribution center, and from the distribution center to the retailing section. And those 2 types of transports, the distance were given with respect to those transports, and we have calculated for that also. And in total, we were able to find out up to the gate, we are able to find out the energy which is equal to 2.26 megajoule, and the total CO2 per functional unit, we found it as 0.11 of per functional unit.
Okay. The design decision matrix. So we have considered a lot of design criteria or objective, starting with reducing embodied energy, like we saw in the previous this diagram. So the materials and the manufacturing that contributes to most of the energy or the emissions. So our design criteria, we've started with reducing the embodied energy and reducing GHG emissions. So these two criteria will mostly be associated with the material and the manufacturing stage. And we also have other objectives, like during the use phase, we have the function, heat resistance, spillage issues, then strength, food safety, ease of use by the user, durability and aesthetics. Then as far as end of life is considered, the criteria would be to reduce the waste that is generated, then also ease of material segregation for further recycling, and also the total recyclability value itself. So the weightage that we have assigned to the criteria is like I've just considered a total to be 10. So among that, from the earlier calculations, we have assigned more weightage to the reducing embodied energy and reducing GHG emissions. And for the recycling or the end of life, we have given the second most weight. And for the use stage, we have split the remaining points and then given weightage accordingly. So ideas, we've taken 6 ideas. So one is using bio-based material instead of aluminum. Here we have considered the case of using mushroom packaging material that's taken from mycelium. Then the second idea is increasing the recycled aluminum content in the container itself. The third idea is water-soluble adhesive to bond the LDPE with the paper carton cover, so that when we are recycling it, the paper component can be taken away easily and the LDPE can be sent for recycling, which is not very easily possible right now. The fourth idea would be, instead of using LDPE, we can use thin food grade paper like waxed paper or bio-based coated paper. The fifth idea is incentivize the reduction in food price. For example, when people are bringing their own containers, so when we price the food, we price it along with the container. So when people bring their own containers, then we reduce the cost of that aluminum container so that people get back something and they're motivated to bring their own container. The sixth idea would be to not use single-use containers, but then make more durable containers with aluminum or with any other material, so that the container stays longer in the system, contributing to circularity. So when we did the multiplication and filled up the table, so you can see the total scores in the bottom. So the one that gets the highest score is the fifth idea. So the idea is to not use containers, but incentivize or encourage people, users to bring their own containers, so that we avoid the use of single-use takeaway containers. So that gets the highest points. The next is the increase in recycled aluminum content. This again, directly goes to reducing the embodied energy or the material that goes into the making of the container itself. So that has more weightage after that. Then also there is the third idea would be the idea 4. So we are completely avoiding the use of LDPE, and then we are using bio-based or waxed paper or bio-based coating, so that we are avoiding plastics from in the container usage, making of the container. The other ideas come below. Interestingly for me, the mushroom based packaging did not get high scores. I was expecting it to get higher scores, but when I did the calculation, it did not, because it had lost lot of points in the usage category. For example, it's not very heat resistant. It gets greased up, it soaks up the oil and all of that. So because it has lost points in the usage category, it did not get more points like I had expected when we started doing the table. We've also attempted to try the same methodology for the single-use container made with paper. The container also with paper, and the tray, it's also completely made with paper, but we have completed only for the aluminum container in the interest of time. Yes. Thank you.
From the calculations of energy, we could find that the virgin aluminum that is being used, it is coming around 70%. So, but when it is recycled, as of now, from the problem statement, we were using 40% recycling. So, when we use the recycling, we are getting the energy a higher order, like from 2 ton, it is moving to 7.85. So if we can increase the recycled energy, that is going to reduce the energy, embodied energy, and the carbon footprint to a greater extent. That is what we found out. Mainly the virgin aluminium is contributing the larger percentage in terms of the energy.
So among the ideas that we have, the idea 2, 3 and 4 come under optimizing the solution. I didn't want to put more colors, so I did not add it. So idea 2, 3 and 4 will be optimizing the existing solution, and idea 5 would be redefining the problem. Idea 5 and 6. So the one that got the number 1, the mushroom based thing, would be re-engineering the system. So the one that got the highest point is redefining the problem. So which means we should stop using single-use aluminum takeaway containers.
We are going to present on life cycle assessment, comparison of emission characteristics of gasoline and EV car. So our goal is to calculate, here we decided on calculating the CO2 emissions, and we compared with average Indian status, US status, New York City and particular Tamil Nadu condition also. Functional unit what we have taken here is the 10,000 kilometer of driving. System boundary from gate to grave. We have included the utilization phase, maintenance and end of life, and we have excluded the manufacturing process incurred while making the car, and the manufacture and the procuration of fuel, branding, marketing and the infrastructure whatever is involved. And vehicle type, small size car we have taken. So fuel source for the EV, it can be from solar, natural gas, wind or nuclear, but we have not gone in depth to that. And we have taken only from the charging and the driving of the vehicle. And same here for the petrol car, fuel is from coal to crude oil and to petrol, but we have taken only the driving part. We have considered the maintenance is to be likely similar between both the cars, and end of life also we have assumed that dismantling, refurbishing, reusing of the car parts, battery parts and the engine are similar. Moving on to the data set, Giridhar will explain.
So this is the data set. So what we have, so for New York City, so we have this is basically the electricity grid mix. So of the the different sources from which the electricity is derived. So this is the main table, and for Tamil Nadu alone, we just have the total emission. So directly the CO2 emission. So based on, so what we did is we assumed some other data, like we have obtained it from the literature and some websites as well. So for first thing is the carbon dioxide emissions from the various electricity source. So we have, what we have got is the for particular 1 kilowatt hour. So what kind of sources from which the electricity is derived, that is in the first one. Whereas the other table what we have got is this is for finding out the total carbon dioxide emission from each of the particular source. So multiplying that, then we will be able to get the total carbon dioxide emission from each of the source. And for gasoline car, it's assumed that it's going to give a mileage of 20 kilometers per liter, and for electric car it is 5.8 kilowatt hour it consumes for going for a kilometer. Then in the case of gasoline combustion emission, and we have extraction emission. So basically gasoline, once you procure the gasoline and use it in the vehicle, that particular only in use phase it's combustion emission, whereas the amount of CO2 emission which comes from taking the fossil fuel extraction, other things, it's accounted in the extraction and upstream emission. So these two must be added to get the total gasoline emission from the starting of the fossil fuel until the use phase.
Here we have the emissions for the gasoline, and when we look into the graph, like almost same for the every regions, because like the process and methods are the same for the in the global content set. And unlike for the EV, like the gasoline vehicles are not benefited by the renewable sources. So this is the total emissions for the EV vehicles. When we look into the graph, like India is having more CO2 emissions because of the coal dominance, and most of the people are looking into the emissions of the EV vehicles, not from the coal emissions. Most of them are looking for the CO2 emissions, not about the local pollutants also. The stakeholders and policymakers are also looking for the CO2 emissions as it is only contributing to the global warming. But local pollutants like CO2, NOx and hydrocarbons are also causing more causes to the people, but most of them are not considering these causes. But there is a framework called Extern E from the European Union. From the European Union made those framework. They have quantified the externalities from the coal-based emissions and also the emissions from coming out from the gasoline vehicles. So they have quantified those externalities in terms of cost. So when you look into those costs, like it goes almost, for the CO2 is almost 0.66 rupees. I have converted, have quantified for the Indian terms, it's 0.66 rupees per kg of emissions. But for the other emissions, local emissions like particulate matter, it's almost more than 800 to 900 per kg of emissions. So like that for the CO2, for the SO2 and NOx, it's more than 300 or something. So we have to consider all those stuff when we are making the policies and stuffs. So other than the India, when we look into the United States and New York, they are onto the natural gas and renewables, so the emissions are less. And also when you look into the Tamil Nadu, they are more into the wind and solar penetration, so the value is much lesser than overall India. And this is the electricity mix contribution for the EV. And also when we look into the electricity mix, the percentage are almost 76 or something. But when we look into the renewables, you can't even see for it's very less numbers in numbers. And also when you look into the India, like it's completely dominated by the coal, and New York State is having like natural gas. But even though the natural gas is like better than the coal, but still it's emitting CO2. So it's better to move on to the renewables rather than natural gases. So, and this is the comparison of the EV and gasoline car. As you can clearly see, like in India, driving gasoline car is better than the EV vehicles, as it emits lesser than the EV vehicles. So this is the data. And for the United States, New York and Tamil Nadu, the EV seems good, and because of the CO2 emissions which you calculated. And also like it's not about like saying sustainable, it's like being sustainable, as we say, like more in Tamil Nadu, like in India, like everywhere they're promoting EV as a sustainable vehicle. But when we look into the data for the Indian context, it's like completely contrast. So we have to think about that stuff. Thank you.
So I think we all had a intuition that EVs are very eco-friendly, or driving EVs will contribute great to our nature. So I think it is from our results, I think it is sort of a greenwashing. It was you all, I think, may have understood that it is sort of greenwashing, or I think the policies are not up to the mark. So that first we need to put the renewables in place to make the electricity, and then promote electric vehicles, rather than first promote the electric vehicles, then put all the renewables into the grid. So I think from our studies, we have already concluded, I think we had made a good conclusion that this electricity mix, that is a major part which contributes to any country. So if we go to the all other, and also the fuel economy of a car. So it is always better to drive a economical car than rather going for high-end cars, which is having less mileage. So that is a thing. So we need a solution for this. So ultimate solution is that we all need to reduce the number of cars in the road. That is the only solution we have. And ultimately, it is as told and studied in this session, it is the end use, and also the education, everything needs to be given to the end user. It is not that we can produce whatever thing even if we whatever branded names we give, if you increase the production, that is not the solution. Ultimately we need a checkpoint at the consumer end, that is reduce the consumption. And that is a difficult part also as we studied. So I think we all should aim for that. And as a local solution, what we aim is that we need to promote EVs in such a states that where the electricity consumption is more towards renewables. Example, in Kerala, I think most of the electricity is produced by hydropower. That is a renewable source. So I think there in Kerala, we need to promote EV vehicles, give subsidies for that. We have seen, I think, all Delhi governments, all the governments giving more subsidies to EVs. Actually, rather it is more polluting to the environment than it is giving any results or reducing greenhouse gases. So I think it is a global problem, but it is a local solution, and it is all depends on the state governments and where to promote the renewables. Okay.
There are some things which we could not quantify. So the thing is, in some cases we assume that the things are kind of similar. For example, the traffic. So in city, the mileage varies in comparison to driving in highway. And for a country average, it depends on whether we are considering more city or the driving more in the highways. That is something which we have to see. Then the car, like washing of the car, like the maintenance part, and the different internal parts, like this is user maintenance, and then we see the maintenance of the car, those parts. So those are something which are pretty different in comparison with like electric and gasoline car, like gearbox and other things would vary. So we kept the things to be same for both the cars, like gasoline and electric car, and we assumed it to be 2 passengers for driving 10,000 kilometers. Since the passenger count is not varied, so I think it is fine. So the main difference what we could understand is basically the electricity grid from which the different sources of electricity from which the power is derived. So in India, it's predominantly coal, as we saw in the previous slide. It's basically coal which is the highest, whereas in Tamil Nadu it's a little bit more of renewables. It's not that coal is lower, but it's just that renewables are a little bit higher. So that is why we could see that the impact on the emissions, like the emissions have decreased. And one more thing what we can observe is in India, like if we compare, so India has like 1,500 for EV, whereas in case of gasoline it's 1,300. So sorry, 1,100. So it is like if we see compare both of these, it's better to drive gasoline. Whereas in case of Tamil Nadu, if we see, it's the other way. It's better to drive gasoline car than EV. So the correction which we have to make is, if we have to bring in EV, so 2 things we have to do. One, we have to make sure that the power is derived from renewables, and the other thing is to focus on like whether we can if all the cars driving in the country goes into electricity, so whether it's at this point of time, do we have the infrastructure to support that much electric power requirement? So that is also we have to think, because we have a huge volume of cars in our country, so we have to think in that aspect also. But infrastructure part things are not considered here, like the infrastructure needed to develop all that, and the car manufacturing is not included.
Actually, for cities, what is happening is that in Delhi, what they're planning is that they're trying to remove all the pollutants like NOx, VOCs, all the pollutants from the city, but it will cater to some other place. Okay, that pollutants will be even more. They have to emit that pollutants somewhere else. Okay, and carry the electricity here to the city. So it is not a all solution to the country, but it is local solution. That's all. So for a city, it will be a local solution, but for a country, it will not be a solution.
But in comparison to gasoline, like the thing is, in city the driving speed is low. Like we can because of the traffic, we can drive only 20-30 kilometers per hour, like average. So in that case, gasoline is fuel efficiency is very low, because we can only drive in the second and third gear. Whereas in case of electric, it depends. It's not dependent on the speed. So lower speed is actually more economical than higher speed. So that is why one way electric car would be better, because of fuel efficiency would be good. Other thing is the pollutant emission directly from the car would be less. So the concentration of pollution into particular city, that would slightly be varied. But as he said, the pollution again, the electricity pollution comes from the other place. So the pollution gets distributed instead of being concentrated, but the pollution is still there. So that we cannot remove them.
Good morning, everyone. Our presentation is LCA comparison between electric hand dryer and plastic paper dispenser. Our team, we are a team of 4, myself Shreya, Niranjan, Ramesh sir and Kavin. Okay, through this LCA analysis or presentation, we wanted to answer one simple question. What environmental impact we are doing by drying our hands? So which is better, using electric hand dryers or paper towels? This might look like a simple choice, but when millions of people make this choice every day, it makes a big difference. So let us see what we are comparing first. Electric hand dryers and paper towel. An electric hot air hand dryer is an electrically powered device that blows hot or cold air to remove moisture from our hands. Its components include motor, heating element, sensors, wiring and casting. Then paper towels. Paper towel is a single-use disposable absorbent sheets made from virgin or recycled pulp, typically dispensed from a wall-mounted unit and discarded after one use. Okay, now let us look at the specifications and number. So a typical hand dryer is about 12 kg. It is mounted on the wall in the restrooms. Its lifespan is around 15 to 20 years. We can take. It consumes around 1800 watts of electricity, and drying time is around average 15 to 30 seconds. And the paper towel is it has 2 components. One is the plastic dispenser and the roll of paper inside it. So the weight of the paper towel might be around 5 grams. So it is sourced from pine wood. It can be virgin wood or recycled. So how we are comparing is, if the hand dryer is used 50 times per day, it is equivalent to for 20 years, it is equivalent to 365,000 paper towels thrown away. So that is the comparison we are going. So now to see the overall environmental impact, we need to first understand the overall system. So this is the overall system of the hot air hand dryer. First, raw materials like cast iron and steel are extracted from mines. Then they are sent for processing and refining to make it to a suitable form for usage. Then the component it is sent for component manufacturing, where individual components are manufactured, like motors, heating elements, sensors are manufactured separately. Then it is brought to the assembling unit, where all are assembled into one single unit, a hand dryer. Then it is finally packed, stored, then quality checked. Then it is sent, distributed, where the wiring and final assembly happens. Then after usage, maybe after the lifespan of around 20 years, it is finally sent to landfill. Since this is an electric hand dryer, it consists of sensors and wires. The final waste can be considered as e-waste. So landfilling it is one safe option rather than recycling or any other end-of-life options. Next is the paper towel life cycle. For the paper towel, the raw materials are pine wood and water. The pine wood trees are harvested, debarked and chipped to get the wet moisture fiber, which is then sent for processing and refining of the pulp. Once the pulp is formed, it is sent for the sheet formation, where it is pressed and dried, and the final paper towel is formed. Parallelly, the plastic dispenser is manufactured from the PP pellets, polypropylene pellets. Then it is assembled into one unit, and the finished product is full of it. Okay, yes ma'am. Okay, yes ma'am. And the end it is sent. The final end of life options are incineration, recycling, and disposal. Incineration of paper towel is much recommended because energy can be recovered, whereas recycling is energy intensive. So next, it will be proceed, sir.
Thank you, Shreya. So we'll get into the core part of the LCA of our paper towel versus the hot air dryer. The functional unit, we have spent a lot of time in deciding the functional unit. Initially, we decided with the per or quantity of water gets evaporated while washing, and or the electricity consumption while using the electric hand dryer, and doesn't work out. But the one which we agreed upon, and finally that will be pretty much like common to both the paper towel as well as the hand dryer, is the one pair of dried hands. So we keep that as a functional unit, and we compare this paper towel and the usage of paper towel with the electric hand dryer, and then we'll compare its usability and also its the functional usages. The system boundary we took is like the cradle to grave. I'll summarize the entire idea in the form of a tabular form. Like I've divided the life cycles, the materials, the processing, the transportation, and the use phase and the disposal. Disposal, there are n numbers of ways you can dispose a product, or you can actually do a multiple way in which you dispose. But for this example, for the ease of computation and ease of comparison, we have compared landfill as our disposal mechanism, and in the future slides for the enhancement feature of the particular the comparison, Niranjan will be explaining how we can use with the other methodologies. And this the data we take it from IdeaMat. It is the LCA database which is shared to us, and we considered the first table talks about the paper towel, which talks about the components, the papers, and the polypropylene plastic dispenser, and the manufacturing and the transportation. And in use phase, there doesn't much consumption of electricity or any energy. And in the disposal, we consider as a landfill. Similarly, we considered the same mechanism for for ease of comparison with the hot air dryer, which we have considered the materials of the cast iron as well as the steel. And then the processing, which for the manufacturing of the cast iron steel, it's just the casing for our hand dryer. This is a wall-mounted hand dryer. And the transportation is from the problem statement. It is 2,000 kilometers, which is 32 ton truck capacity. And the electricity consumption, this is a peculiar data, which we in fact take it from IdeaMat, which we never realized that there is some data for Indian scenarios. We considered the electricity consumption for Indian scenario, especially the Tamil Nadu scenario, and we for the ease of comparison, we just kept a disposal as our landfill. And these are the energy consumptions, and followed by the carbon footprint in terms of kilogram CO2 equivalent per functional unit, and stratospheric ozone depletion in terms of Dallas per functional unit, and ecotoxicity in terms of species year per functional unit. We also consider the water footprint in terms of liters per functional units. Next, I'll hand over to my team, Mr. Niranjan.
Welcome to the interpretation and comparison, where drying hands feels like a climate decision where we need to choose paper towel or the hand dryer machine. On one hand, we have this soft paper towel which is much absorbent, and also it makes us feel that we can take it once and just dry off our hands and put on the dustbin. And only when you realize that the paper dustbin is going to erupt like a volcano with paper towels flowing out of it, which creates a nuisance in the restroom. On the other hand, you have a plush machine which is blowing hot air into your hands and drying off the water. It feels that might be better than the paper towel, but let's see what fares better in terms of environmental comparison when it is made. So let's get started. First we can see the global warming potential of each life cycle stage of the hot air hand dryer. We see that the use phase occupies almost most of the global warming potential of this particular hand dryer, and which is a telltale sign that the electricity carbon equivalent that is generated from the electricity is much more important when we are considering the global warming potential of using the electric hand dryer. And when it comes to the paper towel, you can see when the paper towel is disposed of into the landfill, which is more likely to happen than being incinerated inside the waste to energy plants, like in the case of India, if you can see that the disposal stage has a larger margin of carbon emissions compared to the material processing stage. I checked this bar graph thrice and I came to know that this is probably due to the methane emissions which are generating from the landfill, and the methane is 28 times more potential than carbon dioxide in terms of creating global warming. And based on carbon footprint, I found out that the paper towel has 81% higher carbon footprint than using the hot hair hand dryer when considering the end of life to be disposed of into the landfill. And the water footprint of paper towel is 440% higher than using hot hair hand dryer. But wait, there's a caveat. In the question that was given to us, it is assumed that the paper towel is being sent to waste to energy plant and getting incinerated, where we can recover some of the energy that is being embodied within the material. So the disposal provides us some energy credits, as you can see in this bar graph, and it tells us that using paper towel is much more environmental friendly when it is incinerated at the end of life, which is about 85% less carbon emissions than the hot air hand dryer. But the good news is that we have recommendations for improving both paper towel and the hot air hand dryer. First, when it comes to the paper towel, we can make it better in terms of end of life incineration, and also using other sources of materials like water, hyacinth, bamboo, or agricultural residues, and also incorporating some amount of recycled paper into the paper towel system. And next, when it comes to the improving the hand dryer, of course, we have to increase the energy efficiency of the motors that are being used inside the hand dryer, and also source electricity from renewable sources. We can also have a solar panel over the public restroom so that the power can be generated from renewables. And also we can use metal scraps to make the metal casing of the hot air hand dryer and extend the lifespan of the hand dryer by introducing modular design into it. Let me call Kevin to conclude the presentation.
Hi guys, I came to conclude from the presentation we have came that hand dryer has overall carbon footprint and water footprint when it both are came to landfill. While in case of incinerating, paper towel has a lesser global warming potential than hand dryer. The use phase has dominates the environmental impact for hand dryer, and material disposal period dominates for paper towels. Transportation and manufacturing impacts are minor for both the hand dryer and paper towel impact can be significantly reduced by using recycled materials and using water hyacinth for paper making. Then for improving the hand dryer, we can move to renewable energy usage and changing of motors. Thank you.
Good morning, everyone. So today we are going to be talking about comparison between CFL and incandescent light bulb. So this is our table of content, and we have compared between CFL and incandescent, and our functional unit was 800 lumens, but it was given for 5,000 hours. So for the ease of calculation, we have taken it as 10,000 hours. Now, George would talk about the process flow of both the bulbs.
Okay, good morning. So in our analysis, we considered the upstream, midstream, and the downstream. The upstream included the material acquisition, and the major materials that are used for CFL include glass. So in the acquisition, we consider the glass production, the chemical production such as the sulfuric acid, the nitric acid, and the ammonia, which are used to clean the glass surface before coating. Then, of course, the industrial gas production and the mercury, which is also used, and then the electronic component for power correction. Then, of course, the polymer production. So in the midstream, which is the manufacturing, the main activities here include glass shaping and forming, then fitting of the tube, then the coating, where phosphide is used, and then the filling with the mercury, and then electronic component. Then we have the assembly and the packaging. Then in the use phase, here we try to calculate the energy consumption. The power rating for CFL is 13, and the lifespan of CFL is 10,000 hours. So if you do the maths, we are getting 130 kilowatt hour. Then in the disposal stage, we realize that most of it goes to the landfill, but some, just a small portion is being recycled. But due to facility limitation, this is most of it goes to the landfill. The incandescent, again, the same process. So the major materials include glass, aluminum, and then the tungstens. Then at the manufacturing stage, we have again glass shaping and also the filament making, which is made of the tungsten. Then assembly and the packaging. Then at the use phase, the power rating of one incandescent lamp is 60 watts. So the lifespan of incandescent bulb is 1000 hours. So therefore, it means that for us to achieve the 10,000 hours, we need 10 of them. So if you do the maths, we are getting 6 megawatt hour. So at the disposal stage, again, most of it goes to the landfill. But again, you realize that there are DIY projects such as the miniature terrariums and also for decoration. So, but just a small percentage. Or maybe my colleague will go to the LCA modeling. Thank you.
So yeah, we'll get into the LCI part. So we are here comparing 10 incandescent bulb with one CFL. So we majorly have from the data that was given to us, we have taken the resource acquisition till the product processing. We have not entirely done the product manufacture, only till the product processing. So for the incandescent, if you see, we are using aluminum, glass, a tungsten, and the paper packaging which is used. So from the data that we got, we have applied the carbon footprint, and the total we get is like 1.7029 kg CO2 equivalents. So if you see the usage phase, the electricity use which was calculated previously, we have converted into megajoules, and then if you find the total CO2 equivalents, we get 3,738, which is like way bigger than what we are, from the resource acquisition part. So it is very much visible that the major contribution to the CO2 emissions are from the usage phase. Similarly, in the CFL bulb, so here we are just using one. So if you see the masses and values are pretty much very small, and the total CO2 equivalents that we get from the resource acquisition part is like 0.0125, whereas the usage phase, the electricity consumed is just 130 kilowatt because we are just using one bulb. So the total we are getting is around 80. So just comparing both, this side we have the incandescent, 10 incandescent bulb with one CFL. The total electricity of the emissions from the usage phase is almost 46 times of what a CFL can do. So it is 46 times more when compared to a CFL bulb. So next we have done LC impact assessment from the data that was given to us. So if you see in the CFL part, the major contributor is the mercury, and following that we have lead and a little bit of copper and the metals that is used for forming the bases. So in the incandescent, if you see, it is only the metals that is contributing a huge amount, that is aluminum and tungsten, which is the extraction processes and refining, that contributes to the higher resource use. So overall, looking from here, a conclusion that we are getting is that mercury is highly toxic, and that is what is the major problem that we are facing in a CFL. Though it has a very less emissions in the usage phase. So a small question to all of you: do you think there is no mercury emissions from the incandescent bulb? Because like we are not using any mercury in the manufacturing process. That does that mean there is no emission? So that is where there is an eye opener here. The if you see in the this is a data that I got for US, and it's old data. It was around 2008 from the coal fired power plants. When we generate electricity, we are getting around 0.016 mg of mercury per kilowatt hour that is generated. So if you take for the incandescent bulb, where we are using high amount of electricity, so as the kilowatt hour is higher over there, the mercury emitted from incandescent is way higher than what we think is from the CFL. So this gives an eye opener. Like, it's not only the the materials that you put in, but also the type of electricity from where it is getting generated. So if you see, this is for US actually. So for India, I have just a small data. It is around 0.18 to 0.35 mg of mercury per kilogram. So what are the ideas? So what can we do further? Just a small share.
So for ideas and recommendation pertaining to incandescent as well as CFL, so incandescent should be made in a way that disassembly is possible, because most incandescent bulbs goes into the landfill because manufacturers or recycling companies find it difficult to disassemble the product and use the product in separate processes. Again, incandescent bulbs and as well as CFL should use more recycled material. Even though CFL is made in a way that it can be recycled, they are not recycled into other light bulbs. It just goes into other manufacturing of other products. And for incandescent light bulbs, a university in New York, they had found in 2016 that nano engineering of photonic coatings inside bulb, it helps produces another source of lighting, but then there are no further updates on what happened in that front. For CFL bulbs, again, as I said, better infrastructure is required for the proper disposal of CFL, because in India, most CFL just ends up in the landfill, and because it has hazardous materials in it, improper disposal it impacts the health. Then again, reduction or replacement of mercury, and the final idea was that to increase the amount of recycled glass that is present in CFL.
So we know that the use phase is where the major problem lies in. So just a few suggestions. First is, we have been discussing product as a service as a sustainable solution throughout our course, right? So light as a service could be, you can put front that idea. Then switching to LED bulbs, one of the, because the electricity consumption is less and mercury is not used in the manufacturing process. And one important thing can be renewable powered. So we saw that though even if LED is used, if it is used from coal-fired power plants, the electricity is taken from there, again mercury emissions and other things will keep happening. So moving towards renewable power is really important. Then smart lighting controls, having IoT, sensors, inclusion will help us reduce the wastage of energy used in lighting. And designing of building in such a way that we use the natural lighting rather than depending on artificial ones. And this is the final design matrix. So we have 4 ideas taken: switching to LED, smart lighting, daylighting building design, and renewable powered. So considering 4 parameters: energy reduction, cost, and environmental safety, where toxicity and everything is included, and then user experience, we come to a conclusion that switching to LED is something that we are actually practicing over day-to-day lives. And next we should more move towards is that idea for that is renewable powered lighting, which will which is more sustainable in a way that we can do. So yeah, the same. We are just sure sir. Yes sir. So yeah, moving to LED is something that we are pushing forward with renewable energy in inclusion with it. Yeah, thank you.
All right. Well, welcome back. I think we've got most people back. Okay. So, well, thank you for those presentations. It was really rewarding for me, at least, to see what you have accomplished in a very short time period. And when I think about when we first started planning this, the sort of learning objectives from this session, it was that you do life cycle thinking, right? You can think about the whole system, that you have some capacity to quantify life cycle inventory, inputs, and impacts. You can interpret those, and that you can use those results to make informed decisions about improvement. And I would say from all of the presentations, what I saw that you met those learning outcomes, at least as groups. I don't know if everyone in every group got that, but at least all of the groups showed that you got to that point. And so I just want to say I was impressed with what you accomplished. And I was also impressed, even though we didn't ask you to go do research external to what we gave you, many of you did. And I think you showed that it really helped your understanding of the systems when you did look a little bit further, right? We gave you the barest minimum of data just to do, a minimum, but doing some extra research really helped many of you. So I just was wondering if anybody have any comments on the project from your perspective. Was it a reasonable learning activity? Yes? No? Yes. Okay. So I think, I can stand up here and lecture all, we could have lectured and you could have listened to all the external lectures, but it's really until you do it yourself that you really learn. And so that was our goal, is to take some real time to do the activities rather than just talking at you to get you to participate. So I was really pleased with this. And I will tell you, I am going to change the project in my class next fall to use some of the tools that we used here today and some of the findings that you used. So I think that I learned something out of it too. So thank you for that. And I certainly learned a lot about some of the Indian context, which I also greatly appreciate.
Yeah, it was great. I've never even my students are kind of envious that I'm spending a lot of time here, entire 2 weeks from morning to evening. And I think the same with Sue. We all get to see only students once or 3 times a week if you're teaching a class, right? So I really enjoyed learning. In fact, learning also a lot of new things. As we planned also, Sue led us to a lot of tools and resources which now we can use more in our classes. So, and each one of you, I think the enthusiasm was really good, very contagious. All of you, in fact, were showing a lot of enthusiasm from the beginning of the course, like last Monday to now. The energy levels are always high. So thank you for that. That keeps us motivated and keeps us going. So I think we can kind of reflect on what went on over the last 2 weeks. We had lectures. Professor Sue was leading the lectures, and we had covered quite a lot of ground. I would say, a whole semester's course was packed in this 2 weeks, right? We wanted to introduce you to all the concepts, all the tools, and like what Sue said, get you on a hands-on mode through this project and some of the other mini projects you did with, I think Arun worked with you. The SemaPro demo and the lots of tools, SemaPro, Gabby, I think even yesterday Meghala showed. So that is the next step, right? Now you got the hang of what happens, what is important, because software is not everything, right?
there is a saying, you feed garbage, you get garbage out, right? Garbage in, garbage out. So you should know what goes in and also what comes out, how to interpret what the model is telling you and go back. So it's important. It's the high-end softwares are available, Sima Pro, Gabby, and a whole bunch of other things. But understanding the concepts and using the right data and interpretation is key for any decision making. And I think from now on, you will also be equipped to go and read. There are tons of paper. If you have not read any of those, maybe now it will make more sense to you. Go back and when you download journal papers on LCA, and it'll make more sense to you once you have understood these basics. And yeah, I think the other thing we wanted to tell you is about the opportunities out there. If you are venturing into with your basic degree in whatever field you are specializing in, the sustainability component is going to help you go a long way wherever you're going to be, in academia or in a career, because it's going to be the big thing. Already it is, but it's catching up, just like AI and stuff in the computer world. This has application everywhere. So I can tell you examples from our own master's program. Students have started demanding courses like this as part of the regular curriculum because they saw the job market. Right now, campus placement is going on. Even in this building, you might have seen a lot of sessions happening. So just yesterday, my master student, she messaged me saying that she got into ExxonMobil. She got placed because she was able to handle the questions because she did a project on sustainability and LCA during the winter break with me. So that's getting jobs, right? That's very important for you all when you graduate. Last year also, my master students, she did a project on LCA of contaminated site remediation, and she got into EY, Ernst & Young, one of the big four consultants, right? So the trend is picking up. So those of you who are worried that you chose civil engineering, that's always there amongst our students, right? They didn't choose, it was given to them because of the ranking, right? In IITs and INITs, that's what happens. So the future is quite bright. Okay, you don't have to regret choosing civil or environmental. Okay, so so go and get as much of training as you can get. There are lots of courses also outside this, and improve your resume, right? That will definitely give you a lot of opportunities when you go out. Okay. Finally, we would like to hear from you. We have done a lot of talking. So just about the course, it need not be like all very nice words, but where you would like to get more, strengthen the program. If you're going to offer this again to another batch, which parts were the best, which parts you would like to know more, those kind of feedbacks would really help us go forward, right? For when we are going to offer this next time. And we have different groups here, undergrads, grads, and people from academia, faculty, and also some from industry. So, we want to hear your perspectives.
And the content was very carefully, meticulously designed, and it was delivered in a way, it was instigating our minds to think, it was not just one-way delivery. So the way the matter was put to us in a sequential way, so that we started, right from the start and going to the big life cycle thinking, the process thinking. So that was very good. And I feel if something can be changed, maybe this can be 2 weeks, although is a long time, but still this kind of thing can even go longer, ma'am. So if people would love to come even for a longer course for this kind of concept, so we would really appreciate if you could spare time for that also. So that will be very good. Although 2 weeks is quite a long time for everyone to spare from their works and everything. So definitely maybe in some other mode, some MOOCs or something like that, we can go for that also. So thank you so much, team. We have thoroughly enjoyed your hospitality also, and warmness, and all the support extended to us inside and outside the class. Thank you so much.
What I have learned, though I'm not from engineering background, I'm from management background, but my research is related to sustainability and circular economy. So in this 10 days workshop, what I have learned, I have come across many such elements which I have never considered before. For example, calculating proper life cycle assessment and other criteria, tools and all. So as a management, sometimes we may miss those areas, but I have realized and also learned from my group team and all of you, because integrating all this together, it's really enriching our learning curves, not only for engineer but also for management and for all of us. And thank you so much for making this compact so all the information that you could provide in 10 days. And in future I would also like to learn more about life cycle assessment of different kind of different kind of products, for example different kind of industry maybe. So I would expect more on that. Maybe in this 10 days we did one workshop of calculation as a group. So in maybe next kind of thing we can make 2 such thing, or maybe at least 3 so that we can know how different industry is contributing in what way, so that we also learn the process more. So here I could learn little bit, but I want to learn more. So one project what I feel is not enough, and as madam also said, like it could be even extend for 20 days. I'm ready to do that. Thank you so much, professor, and the whole team, coordinating team also. Thank you.
Thank you, Indumati ma'am. Thank you, Professor Su. I would like to tell that I am already LC analyst, but from the course what I learned is about life cycle thinking. The first basic step to start with the thinking of the process, the entire process we need to think, how the things going on. Then we should start from like life cycle stages. And from life stages, what LCA gives is the hotspot, as what yesterday ma'am told about, like Melanki ma'am, like hotspots from where we are getting so much emissions. And from this LCA, we will understand those hotspots, do sensitivity analysis, and get back like with better raw materials, like better materials, then do comparison analysis. Then we know that anything will cause the environmental cost, like in emissions will be there. But to be sustainable, and also the sustainability is not thinking going backward. Sustainability is always going forward with convenience. We have to think about the solutions that will not, like yesterday ma'am told, like going on horses, a horse cart. We avoided a horse cart, now we are going in car. This is the best solution for that time. But what about the future? Sustainability is always to think about the future. So what? And I have understand, like I was thinking like reuse is a better option, but have a foundational thinking that reuse is a really good through this course. And we'll take the best thing is that through LCA we will get to know many industries, many products. We will learn about many processes. The best thing, this is for any person who wants to do a startup in future, like is the best thing, because we will get to know each about things like through LCA. So learn many industries through this knowledge. Maybe in coming years we get to know the problems. For a startup, there's like problem identification and the proper execution of that idea. Ideas, many people have 1,000 ideas, but only one gets low. As Santosh said, only 4% startups end up successful. But all 100% people are 100 people who are started are having a good idea, but the execution part and all the components working individually and working at the same time is important for a startup. So we'll take all this knowledge and hope we'll build a startup in future. Thank you.
Like I'm chemical engineer background. I have done PhD here only. So always in the research, the thinking level will be always like like we have seen, there are the flow sheet, there are many blocks. But in the research, if we go in the deep, we will focus on only single block, and we will make it to more effective, like bringing are effective. Suppose if you want to design a the application of catalyst should be more effective applications. It's like completely not like thinking, but the thinking is should be like. So that is the wide spectrum like I have gained from this course. We should think about like even if that might not be effective for the whole system. Bad results into life impact, life cycle impact, all those things. Like life cycle thinking, and if it's something, some process or some any research or something, we need to think of how it is affecting the, whether it is affecting the environment. And I like what I have learned, and if I strongly request, and this, if it comes like regular course or then it will be very good, and it will reach to, if it reach to everyone, like all the students, then it will be very good. Yeah, that I request you all. Yeah.
Oh, okay. Thank you, Susan and Professor Indu. Oh, I need to introduce myself. I am a Kenyan, but I'm in manufacturing. My topic is, I'm trying to analysis of laser-based manufacturing cell. So I've been in my undergraduate was in mechatronics, and also master's was also in mechatronics. So this space. So when I got this opportunity, just starting the PhD, so I was wondering where do I clear to me. So funded by the European Union, so opportunity to undertake a course. A friend with whom I think he come from around here, so it's the one this opportunity, and it has been great. So it has really changed the attitude towards this course. I've started now wondering, is this become so easy to the extent that finish this PhD within? It's now very easy to me. I can start and where to end. So thank you very much. Recommendation would be, maybe if you can have this regular, maybe online, so that can be attended. It's a very good course. Thank you very much. Help me in my PhD journey.
I guess I'm the joke for all of you here, meeting you all, variety, like meeting new people, what they are doing, and being with professors was one of the biggest, I guess it's a blessing, was part of this course. And one thing apart from, I didn't learn how industry is going, but real life I'm now more cautious on what I really think, if it is like how it was usually. Now it's like, oh, so much of electricity, so much of everything is cautious. It's like hitting on in my mind now. This is something that everyone speak, that only these people. So I think it's a basic course that everyone must know and should be there. So and practical visits, like going to the dump site, you see it. It's not just the paper or presentation, but when you see in the real life waste that we are generating, it makes you think more on what you are doing and what is the effect. And so thank you so much for the efforts, and thank you so much, ma'am.
So I am from a lot of courses, like we conduct a lot of since I was a participant, and then of course it was very interesting for me to look at the agenda and want to revisit all of these topics and then be a student again, learn again, and then interact. I think I got 100% signed up for. So I'm really grateful that this course was organized, and when Professor Indumati introduced Professor, said she's an awesome teacher, and I was running between all, so I was not on time for many classes, but I not miss much. And then I was able to follow inside the lecture, and I sat down. I was able to follow what it was very simple. It is all complicated stuff, but it was explained in such a simple way that all of us from very different backgrounds, we were able to understand it. We were able to put it inside a project and then execute it. And I was very surprised and very happy that all of us actually were able to do such a good job at the project in such little time. It was nice to see everybody's work. Everybody's work had so much of detail, so much of thought put into it, and it was organized very well. And I know from the being as part of organizing teams, Bindu, Kritika and Arun, they did a really good job. They were right on, point in telling us information, giving out, explanation whenever it was asked, wherever it was necessary. And I think the group, like Indu ma'am said, had a lot of energy. I have met and talked with almost everyone, and we've made friends and we've got contacts, and networking is part of every such course. So I think we all have benefited because of that also. And yes, more courses will be conducted in IIT, so all of you are welcome to come. So hopefully we'll meet again in some other course. Yes, thank you.
Thank you all for that great feedback. It keeps us going, right? And yeah, very soon we'll be having our IDDD on sustainability and life cycle. It's not yet launched, right? School of Sustainability has plans. IDDD, interdisciplinary program on sustainability. So yeah, and probably for the rest of the students from outside, we will be having more such programs online. We have one for businesses. We have sustainability for businesses already going on. Maybe we should have something like that for the students to take on NPTEL, something like that. So great. Okay, so before we hand over, I think we have got a little gift for all of you. Our give a Thanksgiving and also goodbye gifts. This is part of one of my innovation contests called Ideas to Impact. It's a t-shirt. So I hope it fits all. We have different sizes. I hope we get the right size for you. We've got that size. You got the sizes also from them. Okay, good. So we'll try. Hope. Okay. Before that, Thanksgiving to our TAs. A big round of applause. Yeah, Bindu, Arun, all of you know them by now. Where is Kritika? Kritika is missing. Okay. And for logistics support, Hema, you might have seen her around. And some of my students who joined in our gaming sessions. And field visits and all that. So, they did an excellent job. It took a lot of burden off of me. So, thank you for that. Bindu, who had taken the lead right from the planning of the course. So, she deserves a really big round of applause from all.